Okay, welcome back. We are continuing right where we left off in the previous video. This is still the chapter again on oscillations. This is going to be part 3 PowerPoint slides. This is the second part of it. So this is going to be slide 16 onwards. Okay, we're continuing on oscillations. So we were working on some example questions. So let's go ahead and just start with another example question. So go ahead, take a moment, read through this one and pause the video, write down your answer. Okay. If you have a friend with you, go ahead, take a moment, compare answers with your friend. All right, and pause the video again. Okay, let's work through this one now. Now our shapes have gotten a little bit more complex. When we start adding up our points, what we want to realize is we need to add enough points to do the job. So we may be able to do it every second. You may find out you may have to do a little bit more frequently than every second to get a good picture. Oh yeah, let's switch it over to document camera too. It's going to be helpful. Okay, document camera. So once again, draw your line. If you know it, scoot it over a ways. You don't understand to start at 1. I'm going to go ahead and just start at 1 at like 1, 2, 3, 4, 5, 6, 7, 8. All right, so we are at t equals 2, so we move 2 seconds over. Each one is still moving only at 1 meter per second, so it means it's going to move over 2 squares in 2 seconds. We're going to have it start at 4, and it's going to go to 6 with the amplitude of 1. And our second one, I'd be a little more careful. This one now is going to be 3 wide at the base. So this 5 points, they come over 2, so 5 is going to be at 3. This point here is going to be over 2, so 1, 2, this is going to be at 4. We're going to look something like this. Okay, take a moment, make sure you agree that the rectangle is going to be here, and the other shape's going to be in the bottom, coming over to here. So now, let's add them together. Okay, so we come back through, and at point 3, first off, we know everything that's outside of the 2 shapes is just going to be sitting at 0, right? At 0 and 0, we get 0, nothing new here. Okay, so at 3, we're going to be at 0 and 0, so we're going to get 0. Now at 4, we're going to have a value of 1 and negative 1. Let me back at 0. We got to be a little bit careful, because just a split second before that, we're going to be here. So at this part, we're going to find we're going to have a line that comes up and have 2 points. Sorry, pop-ups. All right, so this is going to run from 0 to 3 up to 4. Now, between 4 and 5, we're going to have a value of negative 1 and positive 1. We add those together, we're going to get 0. But between 5 and 6, at 5, we have a negative 1, we have a 1, which means we're going to be at 0 at 5. Then, as we go from 5 to 6, this bottom line is going to be going to 0. So when we're at 6, this is a 0 and a 1, so we're going to be all the way up here. So this is going to come like this. So as you can see, when we're right in the middle, we're going to be having a half and a 1 to give us our half. Okay, once again, choose as many data points as needed. You don't have to include a ton of them, but figure out how to make your shape. So this shape is going to come along, it's going to drop down, it's going to come back up to 0, then it's going to go up to your max, and then it's going to come back down to 0. So the shape that this most resembles is going to be A. Okay. So the answer on this one is indeed A. Okay, hopefully this makes some sense. You'll have some opportunity to practice this on your homework. So, demonstrations. Normally we would do a series of stuff in class related to this, but unfortunately we don't have any equipment to do. So we're going to try this using an app instead. So we're going to look at this FET, some of the ones you guys use for your homework, and this is their interference at FET. Okay, so what I'm going to do is I'm going to turn on just one faucet for a moment, maybe one faucet, and give it a second to clear out all the other interference from the other drop. And notice that we get a wave. And what I did, this is a detector, this blue thing, and all it does is just measures amplitudes. I put 2 detectors. And you notice that when, let's pause that for a moment. Notice that when this blue one here is at a maximum right there, this black one here is sitting at kind of the minimum value. Okay, and as I allow it to drip, they're moving essentially 180 degrees out of phase of each other. Okay, and I can stop that faucet, and I can instead turn on a new faucet, and it's going to also produce drips that are equally spaced. And I set this up right now that the 2 drops are coming at the same point. Okay, so we have a high and low point on the ripples with 2 faucets. Now I can let both faucets drip at the same time. And we notice our shapes get distorted. Okay, let this run for just a second. What I'm going to do is I'm going to pause this here. And what we notice is this detector here, if I come in the area where it's black, detector, not reading the ends. Well, you can see as I move this along, I'm coming negative, negative, negative to minimum. And when I move here, I'm to a maximum. I'm brighter than I was before. So this is a region where the droplets from this first faucet and the droplets from the second faucet have now added together to a maximum. Okay. And this other detector here is at a spot where the droplets, the ripples from the droplets of the first faucet, have now added together destructively. I should say that. Let me show you. Isolated construction was very negative, so they're at absolute minimum. So now our oscillations are still maxes and mins, but now they're going to be much larger. Essentially, they're going to be twice the amplitude tall and twice the amplitude. The trough is twice as deep, and the crests are twice as tall. Okay. Now just run for a while. You see this pattern that goes back and forth and back and forth. Okay. Now let's switch for a moment from water droplets to sound droplets. Let's turn just one on. So if you take your speakers, say you have like 2 speakers that are side by side to each other, you can hook to your computer. And if you're in a place where you actually have 2 speakers or side by side, or you have 2 cell phones, you can do, you can open up on your browser a tone generator or a function generator kind of thing that produces a single frequency like we were using in class last time, and substitute the same exact frequency. What you'll find is if you have one running, you will hear it around the room. I'm going to pause this just a second. So we can see that here is our minimum on the gray dot, and our black dot is at a maximum. Say right there's a maximum. Okay, and we'll let the 2 run, and they're going to oscillate back and forth. Oops, I paused it. There we go. The 2 are oscillating. I didn't turn it off. It worked better. There we go. 2 are oscillating 180 degrees out of phase of each other. Okay, now I can turn on a second one. So this is what we get if we have 2 speakers sitting side by side. And if we were actually in the classroom, we would do this. And what you notice is that there are regions that we get really large amplitudes. There are regions that get really small amplitudes. And there's going to be regions, you can see the line right here, where our amplitude essentially goes to 0. So let's pause that for a moment and see if we can find a spot. And it'll actually make like clear lines. You see there's a line that runs right along in here. There's a line that's kind of blurry that runs right along in here. Those would be lines that if we had this running, you notice we have almost no amplitude at all. If we had it exactly right we'd have zero. It'd be zero because we're having both waves are destructively interfering with each other. So at home, if you have two stereo speakers hooked to your computer, set them about 6 inches to a foot apart from each other and put them both on the same frequency. Okay, and have them tipped ever so slightly away from each other works better, I think, than having them playing exactly the same. And what I want you to do is get up and move around your room and listen, and you should be able to find places in the room where it gets very, very loud. That represents this high amplitude, the bright spots on our graph. There are spots that it sounds, you can't really hear it at all. So it should sound quiet to the point of almost having no frequency at all. That represent these points, this dark line is where our amplitude has destructively interfered. Now, if you don't have a computer with two speakers, but you got a buddy with you who has a cell phone, you can do the same thing. Now, the problem with cell phones is they don't produce frequency exactly the same. You may hear beats instead, but you should be able to find some regions where it gets loud, regions where it gets quiet, even with your beats. We'll talk more about beats later on, but essentially it's where we get a small mismatch in frequency on our waves constructively and destructively add together, and we get this kind of like wah, wah, wah kind of a sound from it. Okay, questions up to here. And what we'll talk about later is I do two lasers, I get wavefronts from one, get wavefronts from the other, and we get interference with light also. And we will talk about this later on, how this works, when we get into optics. So for now, we're mostly going to focus on sound and things like water droplets. Okay, let's go back and look at the rest of this set of slides. Okay, so we've talked about standing waves previously. And standing waves are just waves that look like they're not traveling. Okay, we did this in lab. We had the oscillator showing up and down, and we could see the waves, and if we took the strobe light on there, you can see the waves actually, they stood still or they moved very, very, very slowly. And this is an effect of superposition. Okay, so the individual points on the string travel up and down, but as far as we can tell, our wave is not really moving anywhere. Our nodes stay nodes, our antinodes stay antinodes along the way. And so it's called a standing wave because it appears like the crests and troughs are standing in place as it oscillates. Okay, so superposition is going to let us create standing waves. And I think we're going to pause right here because this is going to take us more than about 2 minutes to get through. So go ahead, pause this one here, and we will continue talking about superposition and creating standing waves in video 3.